Hello friends, this is Jim with Science Talk. In this video I'm going to discuss Arctic ice. So it's a continuation of a series of videos where I'm discussing ice. I've discussed several on Greenland's ice and Antarctica's ice. And now I'm going to concentrate a little bit more on the Arctic ice, i.e. the sea ice that forms in the Arctic Ocean. Before I do so, I'd like to remind everyone to please subscribe to my channel. Please share the work that I do with others. The information contained here that I share with you I consider to be very important, vitally important to what happens to our civilization. So we need to get this information out to far wider people. I hope you will consider supporting the work I do by becoming a patron at patreon.com/Science Talk with Jim Massa. If you're already a patron, thank you for your support and continued support. Arctic ice depends on 1/2 a degree of heat. 1/2 degree Celsius does not sound like much, but for the Arctic ice, it can make a world of difference. 2 separate studies have calculated what it would take to keep the Arctic ice frozen through the summer months, and thus preserve the polar ecosystem and help contain further global warming. Remember, I have already discussed with you how if you have an ice, if it's covered by ice, sunlight, that incoming solar radiation is reflected off the ice back into space, called albedo. The more ice, the more reflective, you increase the albedo. If you start melting the ice, then you have more open water. The water absorbs the heat. Albedo decreases. That's basically what's happening. Basically, well, it's easier said than done. Fulfill the promises that the 195 nations made in Paris in 2015 and keep global warming to well below 2 degrees C, ideally at 1.5 degrees C by the year 2100. The problem with that is if emissions continue, and most likely they will, even if you were to stop the emissions right now, and it's not likely to happen, there's probably enough inertia in the system where temperatures could continue to rise, sort of like an ongoing lag effect. Now, I know I discussed earlier that with the increased melting of Greenland ice, you could slow down, if not stop, the formation of North Atlantic deep water and thus the conveyor belt. I also did state that there may be enough inertia in the system to at least forestall, delay any major cooling down that could happen from such an effect. Because that conveyor belt is a heat distribution mechanism system. Brings cold polar water to the tropics, warm tropical water to the poles. Shut that down, you're going to have very hot tropics, a lot cooler polar regions could start cooling down, and then eventually ice sheets will start forming and so on. Well, there may be enough CO2 in the atmosphere to continue to trap what we call long wave radiation. Sunlight comes in as short wave radiation in the UV spectrum, radiates back out in the long wave spectrum, the infrared end of things. So there could be enough in there to at least delay. We don't know. This is one of the things we do from modeling. We collect data and so forth and do the analyses. Either way, things are kind of topsy-turvy right now. Now, planet Earth will continue on for another 4.5–5 billion years. It's a matter of what it does to civilization. That's really the question. So, they're saying they want to keep it below 2 degrees C, ideally by 1.5 degrees C. That extra 1/2 degree makes a big difference. At a maximum global average warming of 2 degrees C above the norm for most of human history, the Arctic could become technically ice-free once every 3 to 5 years. Reduce carbon dioxide emissions even further, take greater steps to conserve forests, and keep the global temperature at the 1.5 C maximum rise, and the chances are the Arctic seaways will open only about one summer in 40 years. Now, I've already made some videos where I discussed the importance of keeping forests and not clear-cutting forests being replaced by savannas, because savannas, the biomass of plants is nowhere near that of forests. Therefore, the grasslands cannot draw down as much CO2 as forests, leaving more CO2 in the atmosphere. Glaciologists consider the Arctic ice-free when there are only 1 million square kilometers of floe left. But the sea ice has become noticeably thinner and smaller in surface area over the last 40 years. So what happens? You have, as the oceans cool down, it starts to form. Don't forget, we have, the seawater has salt in it. So there is a thing called freezing point depression, meaning that it has to cool down further before it starts to freeze. And then there's that brine rejection I mentioned in a previous video. So typically, sea ice, depending on the salinity, it will not freeze at 0 degrees C, 32 Fahrenheit. It will typically freeze anywhere from -2 to -4 degrees C. The more salt you have, the lower the temperature has to be before it freezes. So, okay, so you freeze this ice. Now, some of it does not all of it melts every year. Some of it survives. And then you have more freezing. So you can get what we call multi-year ice, where you look at ice flow in the Arctic Ocean and you can say, okay, this ice is 1 year old, this ice is 2 years old, and so on. We can actually see that. But with warmer waters, okay, well, it's going to be more difficult to even reach the freezing point, so less ice will form. And even if ice does form with warmer water, less of it will survive to become multi-year ice. That's part of the concerns here. More than 2 decades, meteorologists and oceanographers have repeatedly warned that runaway global warming, as a consequence of continuing to burn fossil fuels, could bring about an ice-free polar ocean by 2050. Sea ice is part of the climate machine. It reflects solar radiation. That's the albedo I have been discussing. That helps keep the ocean cool. If the albedo decreases because there's more open water to absorb the heat, it warms up. Sea ice doesn't form as readily, and then when it comes out the other side, in the Atlantic side, now we start eroding the grounding line of the Greenland glaciers. But not only that, think about, for example, for the animals. Take polar bears. Right? Polar bears hunt seals. Well, they need ice because they stalk the seals. Seals have to make a breathing hole, and a polar bear will sit patiently waiting for the seal to take a breath, pounces on it. Well, if there's less sea ice, where's the polar bear going to go? How's it going to hunt? So polar bears are being forced to swim greater distances, but now they're in the water. Water will suck the heat right out of the polar bear system. Doesn't matter how well insulated they are, how much blubber, they're going to lose that heat. And as a result, they tire, they get cold, they die. There's been reports of emaciated polar bears hauling up on various shorelines, even attacking walruses. That's how desperate they are. Walruses, in case you haven't noticed, are quite large. They can do some serious hurt to a polar bear. So researchers do know that a 1.5 degree target will deliver some good benefits. It will make a huge difference, for instance, to sea levels, grain harvest, and global fish catches. Now, how do we make that jump? because it comes down to what are the temperature regimes. If the atmosphere gets too hot, a lot of the plants will die. Many of the plants that are used for human consumption have an optimal temperature range. Basically, it's from about 50 degrees Fahrenheit to about 80, maybe 85 degrees Fahrenheit. A lot of the plants that we eat, a lot of the grains. When you get warmer than that, a lot of the plants that do well in extreme systems, many of them are not what humans consume. I'm preparing some stories where we're looking at the quality of rice, which is an important staple for many people around the planet. So we have the issue that you're making the conditions too hot for the plants to thrive. You're going to have crop failure. Now, I can get technical talking about the C3 plants versus the C4 plants. But basically the C3 plants are those that are in the lower temperature range I indicated. The C4 plants are in the warmer, much warmer temperature regime I stated. Like we're talking like over 100 degrees Fahrenheit. And the C3, C4 just refers to a particular aspect of the Krebs cycle that goes on in the biochemical machinery. But it is an important distinction in how it's an evolutionary adaptation to conditions. C4 plants evolved that mechanism to deal with hot, dry conditions. C3 plants evolved that mechanism to deal with cooler, moister conditions. Of course, global fish catches, that can tie into changing the salinity, which might change the osmoregulatory functioning of fish. As I mentioned in a previous video, you might lead to permanent stratification where productivity collapses and fish stocks collapse. So there's a whole bunch of domino effect things going on that could happen. So U.S. and Canadian climate scientists, they wanted to see what that half a degree difference could be. And they worked with different computer simulations, and they basically reached, in essence, the same conclusion. And they published their findings in 2 papers that can be found in the journal Nature Climate Change. The Canadian team calculated that at 2 degrees C, ice-free conditions would happen every 5 years. At 1.5 degrees C, that hazard would drop to 1 in 40 years. At 3 degrees C, permanent ice-free summers would be likely. A second study from the U.S. Scientific team basically came to the same conclusions. And I have a little quote here. I did not expect to find that half a degree Celsius would make a big difference, but it really does, says Alexandra Jan at the University of Colorado at Boulder. So, most people live in temperate latitudes. So they're starting to see some changes from climate change, but they don't see the drastic effects that those who live in the polar regions do. The polar regions, especially the Arctic, is where we're seeing the most drastic, greatest changes taking place. In my many years here in Alaska, I have seen many changes. For example, it used to be that you would get that lovely Siberian high-pressure system sliding over Alaska and the Yukon Territory, and it sets up shop, and for 3 weeks, with that wonderful clockwise flow, no sarcasm, we would be sitting there 50 below or colder for 3 weeks, basically waiting for that system to erode. That doesn't happen anymore. Now we may get some cold air moves in for 3 to 5 days, not 3 to 4 weeks. And when it does, it's usually about 45 below. In fact, for the last 2 winters at my home here outside Fairbanks, I have not recorded a single day in the last 2 winters where temperatures reach minus 40 or colder. Last 2 winters, not a single day. Now yes, 2 points don't make a trend, but it's something. In fact, to go even take that further, the last 5 winters here at my home, I have recorded 23 days where the temperatures reach minus 40 or colder. 17 of those 23 days was from 5 winters ago. So if you now want to look at it over the last 4 winters, it has only reached 40 below or colder 6 days. And two of those years was 3 and 4 years ago, because the last 2 years it hasn't. Things are changing. We're seeing species moving north, including, unfortunately, the spruce beetle, which is destructive. Spruce beetle is typically held to the Anchorage area, because Anchorage is milder. Well, now with the milder winters here in Fairbanks, spruce beetle can thrive because it doesn't get cold enough to kill the larvae. The larvae survive the winter, so now we're seeing spruce beetle infestations up here. I'm seeing magpies, a bird that's found in the Anchorage area, never found in the Fairbanks area. I'm seeing magpies on a regular basis up here. We're seeing a push of the tundra vegetation replaced by willows, because the permafrost is thawing, allowing for plants that require a deeper root system to take hold, as opposed to tundra vegetation. So we're seeing this northward movement. Things are happening. So just wanted to bring your attention to these 2 studies here. I hope you like the information I share with you. Please share my videos with others. Please subscribe. Please become a patron. Thank you for your time.